Good afternoon, everyone. Thank you, Professor Mammeri, for joining us. So Professor Mammeri is a professor of applied mathematics in Camille Jordan Institute, Jean Monnet University. He was the head of the Applied Analysis A3 team and the head of the master's degree in modeling for biology and health. He's a member of the French Mathematical Society, French Applied and Industrial Mathematical Society, and European Mathematical Society. He's the recipient of several grants and principal investigator for 3 ongoing projects funded by NRA, CNRS, and Campus France. His research interests include modeling in life sciences, analysis of nonlinear PDEs, and scientific computing with applications to multiple disciplines such as ecology, medicine, and biochemistry. So today, Professor Mammeri will be presenting a talk on the influence of environmental and social characteristics in SIR epidemic models. Thank you, Professor Mammeri. The floor is yours.
Okay. Okay. So first, so good afternoon. Yeah, still afternoon also for you. So thank you for the kind invitation. So this is a great pleasure to present some of our work on in particular on not a such a good thing about COVID-19, but still okay. So I think also, so I had a look on the other talk. I think my talk is I will share my screen, but so my talk is probably much more simple to understand than the 2 other talk you had the 2 last weeks. So it's really I think understandable for everyone, even people who are not doing mathematics. This is what I plan when I prepare my talk. So this is something open to everyone who just want to understand some of mathematics. So there's absolutely no proof of any theorem. It's just to understand how we can proceed to develop an epidemic model, and in particular, so my title is a little bit a lie, because I will talk about environmental and social only at the very end of my talk. So this is what I plan to do, is just to start with some history of epidemiological modeling. So just to understand where the SIR model is coming from, and then how we can adapt it for COVID-19. And only at the end, I will, if I have enough time, I will explain how we can extend this to take into account, in particular, the space, and also some social category in the spread. So let's just start. So you will see there's no complicated mathematics. So even so, actually there's complicated mathematics at the end, but everything is not written. So you will not see any PDEs in my talk. Nothing complicated. Okay, so let's just start with some history of a mathematical model of epidemics. So I think most of you have learned some French. So just to give, so this is what we consider as the first mathematical model of epidemics. So if you read in French, so there's some clue to find the date of this paper, is the old paper, because so the word vérole here does not exist anymore in French. So this paper is quite old. So this is about the smallpox and the inoculation of smallpox. So the smallpox is an infectious disease, contagious. So it's very old. So it's 1760 So, and the paper was written in French by Daniel Bernoulli. So Bernoulli was not French, he was from Switzerland, but he wrote the paper in French and presented in the French Science Academy. So, and the question of his paper was this one. So what are the benefits of the inoculation? So during that time, we don't talk really about inoculation, but we were talking about variolization or variolation in a population. So today we could call it vaccination. But at that time, we don't call it still vaccination. So how he did that? He did his computation. So the paper is quite easy. So he considered this population of Breslau. So why this population? So this population, there were, so in the 18th century, there were a lot of study of this population because this population is almost constant. So the number of deaths and births is almost the same, and the population is almost constant. So in the mathematical modeling, in the mathematical computation, they will assume that the population is constant. And from the data he had, he was able to compute the probability of getting the smallpox, the infection. So he computed that you have 1/8 chance in this population to get the smallpox. And he computes that you also have 1/8 chance of dying from the smallpox. And also he computes that if you are inoculated, you only have 1/200 chance of dying. So if you look at the paper, so this is the table he gave, there is no computer, so he make all the computation by hand. So, but it's written in French, so here you have the age, here you have the survival individual of age 0, age 1, etc. The one who didn't get the disease, etc. So if I put it in another way, so this is the data from his table. So what does it mean? It means you have 1,300 newborn of age 0 from this 1,300 individual. If I come back, so I look to the age 20, so 98 will be 20 years old. Okay, so this is the curve. So this is the data without any epidemics. So, and then he used what he said before. So you have 1/8 chance to die, to get the smallpox, to die from the pollen, and 1/200 to die from the inoculation. And what gives this computation is the right curve. So there's two important things to see is that, okay, so the right curve is above the purple one. So you have more individual. So the inoculation has a benefit because if I'm looking only 20 years old individual, with the inoculation, I have 77 more people of 20 years old. And the other thing that cannot be seen in this plot. So if I continue my curve till the death of the people, so what you will see also is that the inoculation will also increase the life expectancy of 3 years. Okay, so this is just a mathematical model, but the mathematical model is important to say, okay, inoculation is good because you have more individual and the life expectancy is bigger. Of course, so the paper was not immediately translated into vaccination, but what is also important to know is that the inoculation of smallpox is something very well known from more than 2,000 centuries in China. So they know that the inoculation of smallpox is something that works. But nobody has done the mathematical computation before. Well, this is what we consider as the first mathematical model of epidemics. But this is not still an SIR model. So to come closer to the SIR model, so we need to look at another disease, so which is the plague of Bombay. So the plague is a bacterial transmitted by to human by fleas. So for a very long time we were thinking that plague is a disease transmitted to humans by humans. So in most of the control what you try to control humans, only humans. But when we understand that this is not humans who are giving the bacteria, but fleas, it changes a lot. So, but still, so Bombay, so today is Mumbai in India. So, but in that time it was part of UK. So most of the scientists who work on that were British scientists. So in one of the first who tried to do some mathematical modeling is Sir Hammer. And what he said, so what he tried to do, he said, okay, so we have a population, and I will split my population simply in two parts. So I would say I have one part of individual who are susceptible. So sometimes we say also the healthy people, good health. So, but it's better to say susceptible. So this is the people who can be infected. And he split the second part with the infected individual who are also the contagious individual. So finally, in this population, he has just two groups, the one who gives the disease and the one who can get infected. And so what he said, okay, you are susceptible and you can become infected. So this is his model. And how he translates this into mathematics. So it's not complicated to understand. So what he said, okay, who are the susceptible today? Or who are the susceptible tomorrow? So this is the susceptible today minus the one who become infected. And who are the infected tomorrow? They are the infected today plus the one who just become infected. So the question is how you become infected. So it's very simple. It's just say, okay, to be infected, a susceptible has to be in contact with an infected. Okay, so if I translate a little bit more in mathematics, so I have susceptible tomorrow is equal to susceptible today minus, so I will write like this, the susceptible multiplied by the infected, so the susceptible in contact with the infected plus some coefficient. So why some coefficient? Because so you can be in contact with some infected, but it doesn't mean you become infected. Okay, so the infection needs some efficiency to succeed. Okay, you are susceptible, you are in contact with someone infected, but it doesn't mean you will become infected for sure. Okay, and so if you take so and you do this for every time step. So for mathematician, it's not so complicated. If I just put ST on the left part divided by H and make my H small as possible, and I will rewrite the equation, which is exactly the same. So instead of looking for the susceptible at time tomorrow equals susceptible today, I will look to the difference between susceptible tomorrow minus the susceptible today. So we call that the variation, so the derivative in time. So what does it mean? Yeah, I will write like this. So the variation of susceptible will decrease. So the small omega is the average number of contacts between susceptible and infected, multiplied by some infection rate. Okay. So sometimes the product omega times beta, this is also what we call the probability of infection. So the probability to become infected. Okay, so the one who were susceptible, so there is minus, they become infected, so there is a plus. Yeah, okay, so the one who are infected, we go in, who are susceptible, we go to infected. Okay, so but this is not the only assumption he made. So he say, okay, so there's two equations. So Sir Hammer was not a mathematician. So two differential equations to solve is too complicated. So you make an assumption that was done also by Bernoulli before for doing his simulation of the smallpox. So he will say, I have a constant population. So let's say constant population equal to capital N. So I have a constant population. So if I do that, so I have only susceptible and infected. So I can just change a little bit. So who are the susceptible? So this is, it will be all the population minus the infected. Okay, or the other way, who are the infected? So this is the whole population minus the susceptible. So, but doing that, it's good because, so it's simpler because here I have two equations. So it will change, okay, susceptible, who are the susceptible? This is the whole population minus the infected. So at the end, just have one equation which depend only on the number of infected. Okay, so what does it mean? To know the number infected yesterday or today or tomorrow or in 1 year, you just need to know the number infected today. Okay, here I don't need to know the susceptible. I just need to know the infected. So, so imagine, so all the coefficients you see in blue, red, and green, these are constant number. So, and I just need to compute the infected. So, but lucky for him, so it's not so simple equation because okay, you see you have I, you have parentheses and multiplied by I, so you have a derivative and you have I squared. But lucky, we know how to solve this kind of equation. And it was solved by another Bernoulli, which is not the same as the smallpox, but the same family. Okay, but still, okay, he can solve his equation. So this is the purple one. So these are the real data from the plague. And he tried to make his computation. So again, there is no computer, so he tried to make the computation by hand, and he find this kind of curve. He start again, trying to choose another parameter, and always you have this kind of curve. So again, he was not a mathematician. So this is an exercise. So if some student will watch the video, so prove that all the solution of this equation behave always like that. So because he was not a mathematician, so he was assuming that it is possible, but you can prove using mathematics that the solution of this equation, so you can choose everything you want for the parameter. So this is positive parameter. So you can try to choose everything you want for the parameter. You will always have this kind of curve. So this is a S curve or logistic curve. So it will never go down again. So the limit is this one. So something we're missing in the model. And we wait 21 years to get a solution. So what is the model of Kermack and McKendrick? So they are also not mathematicians. So they start with exactly the same as the previous model. So they say still, okay, you have a population, you have individuals who are susceptible to get infected, you have the infected individual, but they just say, okay, but this infected individual, they can recover. And when they recover, they are not anymore contagious. And they do exactly the same as before. So we still have the susceptible. So the number of susceptible is decreasing. So when you are susceptible, you become infected. When you are in contact with infected, okay, the same. So the new infected are the susceptible who become infected. But now you have this one, okay? So it was this arrow, you are susceptible, you go to the infected. But now you are infected, you go to the recovery. So to recover, you just need to wait. So you wait minus something and you recover. And then you recover. So the gamma is what we call the recovery rate. So, and now we have three equations. So it's a bit more complicated to solve. So you cannot try to simplify saying this is constant. But if you look for the solution of this system, you have three equations. So you have I multiplied by S minus I. And if you look, you can find solution that behave like that. Okay, so this is a bell curve, which looks like the exact data. So, but if you look in the paper, so they are not exactly solving the system. So they just say, okay, what we want is a curve. We want a solution like a bell curve, like that. And so they are they construct the solution looking like a bell curve. And then they show that indeed, okay, you can have a bell curve solution of this equation. So the question is, all the solution of this system are or not bell curve? So, but this is the other way. So they build the system and then they find they were looking only on solution that looks like that. So fortunately for them, it works. So this is what we call the SIR model. So what is interesting in the SIR model, because so you see SIR, so still okay, you have three compartments, you have three equations or differential equations, so it's quite difficult to communicate. So if you have to explain to people that you have to create a lockdown, you will not tell them, okay, you have 10 differential equations, and the equation will say you have to do a lockdown. So you need something simple. So if you look to the system of equations to complicate, so but you say, okay, so you have a large population, and in the beginning of the epidemics, very few people are infected. Okay, so you cannot assume that almost everybody is susceptible, and the number of susceptible is constant. Okay, so you forget the equation. Okay, you forget this equation. You just say S is constant. Okay, so here I have S depend on time, but then I just say S is constant. So I have some coefficient multiplied by I minus some coefficient multiplied by I. So at the end, I just have a coefficient multiplied by I. So this equation is very, very simple. So you don't need to solve a differential equation. So this is, the solution is exactly like that. So this is the exponential function of RT, where R, so the coefficient R is given by this. So we find again our coefficient, so the contact, the infection, the number of susceptible, the recovery. And what does it mean? So very simple. So at the end, you just compute this value. So you compute the number of the size of the population. You compute actually not omega and beta, but the product, so the probability of getting infected, the recovery, and you get a number. Okay, and then you see, okay, if this number is positive, so you have exponential, so the number of infected will grow exponentially fast. If this number is negative, the infection decrease. If this number is 0, so this is constant. So it's quite easy at the end. Okay, I have 2 equations, too complicated. And then I just have a number. And this number is quite simple to compute. But the problem is that this number does not have any biological meaning. So this is just a mathematical term. So it's still complicated, but okay. So, but we can rewrite a little bit this coefficient. So I have this coefficient. But this coefficient, okay, for example, I can put gamma in factor, and this I can rewrite like this. Okay, this is exactly the same. And this term, just this one, I will call it R naught. And I have exactly the same as before, but instead of looking to the sign of the small r, I will look if this R naught is greater than 1. So greater than 1 means that R, small r is positive. So the infected is increasing. If it's less than 1, it's decreasing. And if it's equal to 1, it's constant. But why is it interesting? So let's go back to the definition of this R naught. So what is omega? So omega is the average number of contacts. Okay, so beta is the infection rate. So omega times beta is the probability to get infected. So gamma was the recovery rate. So the opposite of the recovery rate is the duration of infection. So if you want, the recovery is how many days you need to recover. So this is also how many days the infection take place. And here you have the number of susceptible. So you look, so you have the probability of being infected multiplied by the susceptible during the infection. So what does it mean, this R naught? So this is just the average number of new infection during the infection period in a population with only susceptible. Okay, so sometimes people who are using this. So at the end, this number is just a number, simple to compute, but this is the definition. So it will give you the average number of new infection during the infection period if everybody in the population is susceptible. Okay, so this is the definition of the R. Okay, so and then how we can adapt all this history to the COVID-19. So we not remind what is the COVID, everybody knows, but still, okay, so COVID is an infectious disease. So in France, the first case, the first official case is January 24, but we know that there were cases before than this day. And the World Health Organization declared the emergency only on January 30. So, but if you look in the literature, there were already some scientific paper in 2019, mainly in China, who were trying to model this new epidemics. So, and what was the very first model of COVID-19? It was exactly the same as we have seen before. So most of the model for infectious disease are based on this Kermack-McKendrick method. But the very first model you can have a look on the literature, also on COVID, was based on the SIR model. So they split the population in 2 parts: susceptible, infected, and removed. And they use exactly the same equation we have seen before with the very first data they get and make the simulation. Okay. And then, so what is also hidden in the computation? So if you want to control the epidemic, so if I look just to the graph here, so what does it mean? So to get susceptible, so you are susceptible, you become infected, and to become infected, you have to be in contact with infected. Okay, so to control the disease, in theory, is simple. Just avoid contact with infected. Okay, so it means you will break this arrow. So because the first study were based on this model, so in China they use this model, and then they say, okay, you just need to avoid contact with infected. And very early in China, they did a lockdown. So in the end of 2019, they were locked down in China. But still, they saw that it doesn't work. So what is wrong? The model is wrong. The way to control is wrong. So during that time, we don't know. So the question was, is there some other transmission routes for the COVID? So one of the very first paper I have seen for my knowledge, we're talking about a new way of transmission. Is this paper from Danshan is co-author. So forget for the bottom part. So if you just look for the upper part, so you have the susceptible, infected, and detected. So or removed. So this is almost the same. So there's one more compartment, which is the latent. So the latent is you are infected, but you don't know. You don't know yet that you are infected, but you are already infected. So what they propose in their model was what they say, okay, so you are latent, so you are already infected, you don't know. And some will be indeed infected and be detected. And so these people will be controlled, but still there's some alternative way. So look, it was in February 2020. So the alternative way we did not know. So in the paper, we were talking about some environmental routes. Okay, so what does it mean? If you control only the one you detect, okay, the epidemics will continue through this way. So, okay, because he was saying both are still contagious. Okay, so even if you control this one, but this one are still contagious, so it continues. So another interesting model was developed by Liu and his co-author. So they were saying this one. So they say, okay, so you are susceptible and then you are infected, but you have no symptom in the beginning. And then everybody has symptoms, but some are detected or reported, but some are not. And both of them, so they will recover, but both are contagious. So in their paper, so they suppose that this is just a question of being detected or not. And so what we did, so what we assume, so in April 2020, so exposed and latent is the same. Okay, it's just to overword. So what we say, okay, you are infected, but you don't know yet. Then some will have symptoms, so does not have symptoms, and then they recover. And what we assume is that all of these are contagious, okay, with different level of contagion. But you are already exposed, you don't know, but you are already contagious. So you have symptoms, you know that you are contagious. You don't have symptoms, you are still contagious. Okay. So, but in April, actually, we did not know that it was the good way to do that. But in terms of mathematics, it's not complicated. It's mostly the same as before, but okay. But what is the transmission? So the transmission now is not only contact susceptible with infected. So this is contact of susceptible with exposed, contact between susceptible and symptomatic, contact between susceptible and asymptomatic. So, but the idea is actually the original one, not so complicated. So, and then you can write the equation for the exposed, the infected, and the recover. But it's not so complicated. So you see here I have minus. So the one who, here I have minus, here I have plus. So the one who are susceptible, they go inside the E. Here I have minus delta, and then one part is going to the asymptomatic, one part is going to the symptomatic, and then they recover and go in the recovery. So you can try to solve the equation, but we don't need. So what is interesting, okay, you can also have a basic reproduction number that you can split in 3 parts. So you have the basic reproduction number due to the exposed individual, the symptomatic and the asymptomatic. So here I do exactly the same as before. So what is the R naught of exposed? So you have the average number of contacts, the infection rate due to the exposed individual. So E is not the infection period, but what we call the latency period, and the proportion of susceptible. So at the end, you get the average number of new infection during the latency period by the exposed individual, okay? Plus the one due to asymptomatic, plus the one due to symptomatic. So in France, in the beginning of the COVID, it was around 3. So just to explain well, so what does it mean? 3, it means, so if you have 1 infected, it will infect 3 individuals. And then these 3 individuals will infect 3 other individuals. And all these individuals will infect again 3 other individuals. Okay, but what we say at the end, so at the end, so we have a number, it is greater than 1, so the epidemics will go. So this is what was done for most of the country. So, but just to put some mathematics, okay, we can put some mathematics. So if this is greater than 1, so you have the epidemics will grow. And one other interesting thing in the model say, okay, so you see at the end, you have only susceptible and recover. So what does it mean? This theorem, it just say, so if you wait for a long time, very long, at the end, everybody will be, actually it's not recover, it's removed, so it means recovered or dead. So, or susceptible. So what does it mean? I mean, if you wait very long time, the epidemics will vanish. But the time you wait this is a mathematical time. So mathematical time is t goes to infinity. T goes to infinity is not the biological time. So this is interesting for a mathematician, but for real life is not so interesting. Okay. So what happened with the model? So if I take exactly my model and I try to find the parameter and run the simulation. So this is what I get. So the dots are the data for the first 15 days in France. And the red curve is the simulation, the best simulation. Okay, and if you just let run the model with this data, what will happen is this, okay, the blue curve. So you will get 5 million people infected. So if nothing was done. So the very first simulation, so actually the very first simulation were made with a discrete model, not with a differential equation, but with the same kind of conclusion, saying that if you do nothing, a lot of people will be infected, and so a lot of people will die, so you have to do something. So in the question in the beginning, if you remember, the question was how to flatten the curve. So many things to do. So and how to flatten the curve, so you have to come back to the definition of the R naught. So the question is, okay, I have this R naught, so in the beginning in France it was 3, so 3 is greater than 1, is not good, so I have to make it less than 1. I have to do everything to make it less than 1. So if I look to the definition, okay, I have to reduce this number. Okay, so if I want to reduce the duration of infection, or if I want to improve the recovery, we need treatment. So, but in 2020, treatment, we don't have. If I want to reduce the number of susceptible, it means I need to increase the immunity. So I need vaccine. Oh, this is vaccine, but there is no vaccine. So the infection rates, you cannot play on this because it's depends on the virus itself. So you cannot do anything on beta. So what it remains is the number of contacts. So if you want to reduce, but you reduce the number of contacts. So you don't have treatment, you don't have vaccine. What you do, you reduce the number of contacts. So you impose, for example, lockdown. So the effect of lockdown in France, so this is the simulation. So what you will get, so you will get this kind of decay of the R naught. Okay, and the question, so we did that before the end of the lockdown. So what will happen at the end of the lockdown? So if you continue the lockdown, it will be that. So if people respect the distancing, so it will mainly depend on the distancing. So, but this one was done before the variant. So we were assuming that you have only one straight of virus. So what does it mean? Okay, in France, actually, you need to respect more than 63% of, well, more than 63% of the population have to respect the distancing rule, which is not so. Okay, so I will not. So why? Okay, why the curve can go after the lockdown? Okay, again, so if I come back to the R naught, so I just reduce the number of contacts, but so the number of susceptible is still the same. The infection, the recovery is still the same. The infection is still the same. So when you stop the lockdown, you just increase the number of contacts, but the number of susceptible is still big. So if the virus is still there, the R0 will become again very large. So, and then you go. So many other ways to flatten the curve. So now we know, so vaccination is one thing. So the quarantine. So we did that for some countries, not in France, because quarantine in France, I never did that. And also we did some treatment with the hospital, so this is the kind of simulation you get when you play with the vaccination, with the treatment. So to show you what simulation I did. So this is these three are medical doctors from the Mammeri hospital, University Hospital. So, and they were trying to implement a clinical test for some treatment. And so what we show is that so you don't need a very efficient treatment. So this is for outpatient treatment. So you don't need a very efficient treatment. So what is important is when you start the treatment. So of course, so you know now COVID is mainly 2 weeks. So the treatment has to be in the very 5 days. So if you do that in the very first days, you don't need to be very efficient. So this is what is behind this. Okay. Okay, so 15 minutes. Okay, nice. Okay, so but what is important to understand? So, and I think so. Model of COVID has been used a lot. So mine was not so influential. So the most so the model would change make the most of the government change their mind is a model developed by the Imperial College, and this is a discrete model, agent-based model, but mainly with the same conclusion. And then it was used by the government, by the politicians who are not doing mathematics. And sometimes, and I think most of the time, they forget to give some explanation of how to use the model. So this is very important to understand. So what I showed before are very simplified model. So even the model that has been used for Imperial College, this is not the truth. This is simplified model. And we, for example, in the model I show, I just say, okay, we are all the same. We just are susceptible, infected, or recover. So there is absolutely no difference in our own characteristic, okay? Our age, our gender, or many things. And also there is absolutely no consideration of where we are. So it was one question. So we see now very well that the behavior of the epidemic is totally different if I am in France or if I am in other countries. So, and even inside the country itself, there's a many difference. If you are living in Paris with a lot of people, it's totally different from people who are living in the countryside. So in this model, there's absolutely no consideration like that. And the question was how we can take into account all of this. So age was taken, a lot of people have taken into account the age, but the rest less. Okay, and in the very beginning, we were interested first in the physical environment, the space. So what is good in France is that we have access to a lot of data freely. So this is a two map. So this map is the population density in France. So the more is red, the more you have population. So this is the map, but we have exactly the data. So we have the file with the data. So we have the map with the density of population, so which is something interesting. So because again, so the COVID or all the epidemics I showed here is made by contact between individuals. So the more you have people, the more you may have contact. So the density is something important. And also what we have here on the right part is all the commuting between cities. So here I take the main cities. So this is Paris, this is Lille, this is Nantes. I think Fatima was in Nantes. So we have access to this data. So we know the number of people who are traveling from this place to this place, this place to this place, to this place. And we can have a really nice zoom on the simulation. So what we did, so what I did actually is quite simple. So I used some partial differential equation because now I have two variables. I have the time, number of infected by time, but I have also where are the infected. So I have the time and the space. And then you can compute like that. So you can still have a basic reproduction number, which is exactly the same as before. But what we say in the model, yeah, I forgot to say. So what we say in the model is that, so the susceptible can travel, the exposed, because you don't know that you are infected, so you can travel. The asymptomatic can travel because they don't know they are infected, so they travel. But the rest, they are not traveling. So the symptomatic, they are not traveling. We assume that, okay, they are infected, they stay home. Okay, so this is another way to explain. So this is also something good that we have. So we don't have the number, so during that time, we don't have the number infected per city, but we have per state. So we have this kind of map, so we can say, okay, in this state, I have 9 infected individuals. Okay, so just to show you the simulation. So in the simulation, it's quite simple. So there's two things. Okay, you can travel between city, and you also have the mean daily movement. So a French citizen is moving around his home around 15 kilometers. Okay, so you have the mean movement is 15 kilometers from your home. So this is what is in the model. So on the left is with the lockdown, on the right if nothing was done. So just to see So there's a spatial distribution of the infection. Okay, so here, because we made a lockdown, so the infection don't go to the western part. Okay, so what was, so I did this, so during the lockdown in France, so I don't have a, I wanted to do this before they stopped the lockdown. So this is the official map from the government. So the May 11 is the day when we stopped the lockdown in France. And so, and I did the simulation before, just so I didn't want to cheat. So I make the simulation, and if it works, it was good. But if it didn't, so okay. But it was the simulation much before the official map, and this is the official map on May 11. So, but actually, the true map is more like the simulation than the official map. So, and the question was, okay, so what we were trying to say is that, okay, you don't need to make a lockdown everywhere, because, you know, if you know where is the epidemics, you don't need to make a lockdown here in the western part, because there is no big deal in the western part. But still, we are in the same country, and it's quite easy to move from one place to another. Okay, so but here in this model, so you see this is one main country, and you can travel in the whole country. So what the next question was what happened if you have a spatially separate country, or a country with many islands? Can we do this kind of thing, not for just one country like that, living in his own, so the frontier were closed during that time, so it's quite easy. But you have to have a separate place. So the idea would be exactly the same, but in each place, I will use my model. So, for example, I want to see the spread in France and in Lebanon, and so I will first, so forget the exchange. So I'm looking only in France, I'm looking only in Lebanon, and I need also to compute the person, the one who are traveling between the countries. Okay, so there is some people, so who can travel between the countries. So you need your test. Imagine you are still infected, but you are negative, you can travel, and you do like that. So this is mainly the same idea. In each place you have your model, plus you need the commuting between all these places. So we didn't do for France and Lebanon. So we did the computation for the Philippines, because the Philippines is a country with many islands, so 7,000 islands. So, but we didn't simulate the 7,000 islands. So we just simulate the main island and the main airport. So here you have the airport, and you simulate the displacement between island between two airports. So this is with some lockdown because it's not the same days. But this is, so I don't have the official data, but this is mainly what happens. So the first is it propagates in the south, and then it go back to the north. So the capital is here, Manila is here. So this is the main city, is Manila. So that's why it start in Manila, then they travel, so it's spread in the South Island, invade the south, and then go back to the north. So there's two waves in the, so yeah, I didn't put the simulation, the wave, but there's two waves. So one first wave is going to the south, and second wave going to the north. So in that case, there's only one strait of virus. So there is no mutation of the virus. So with one strait, okay, you can have two waves. So just because of the space, so you travel to the south and go back to the north. Okay, so just to finish, so the question was, okay, so this is space, but there's many other things that can be of interest in this kind of epidemics, not only where you live, but actually, yes, where you live, but in which kind of place you are living. So if you are living in a building, a big building with a lot of neighbors, is not the same as living in your own home without neighbor. So it's something that you need to take into account. But the thing is exactly the idea is exactly the same as before, but instead of saying I am in one place, I will say I am from one social category. I am from another category, and there is exchange between categories. For example, okay, you are living in a city, one group is living in a city, one group is living in the countryside, but the people who are living in countryside, they are traveling to the city to work, and so they meet people who are living in the city. And then you can make a lot of things like that. So it was very complicated because very few data. So what we have, so this is so we need to compute. So what is important is the exchange between the category, social category. So how you know that a teacher, for example, what is the contact of a teacher? What is the number of contact of a university lecturer? Actually, you don't have access to this kind of data. It's very complicated. So in France, the only data we have is the number of contacts by age. So what does it mean? So mainly we know, so if you are 20 years old, we know the average number of contacts you have with someone of age 60. The average number of contacts you have with someone of age 10, for example. So we have access to this. But if you look, so for mathematician, it's quite, so if you look to the matrix, it's very strange because the matrix is not symmetric. This is very strange because if you have contact with someone of age 20, he also has contact with you. So it should be symmetric, but it's not. So there's some problem with the matrix itself. And also, but we don't have the contact, but we don't know what they are doing in the life. So we don't have the contact with a teacher and a worker, for example, or a farmer. And what we have is the proportion of individuals in many social categories according to age. And the question is how you can rebuild or reconstruct a matrix of social contact between social categories. So it can be done. So this is just a linear algebra, it's just a variable. And then you can play, okay, so this is with age, just not so interesting, but a lot of people have done that. It's just to see what happens. So if you play with age, so age is a category, okay, or social category. If you take you isolate only the old people, so which is interesting. So isolated in old people, you reduce the number of deaths. So what does it mean? Okay, so this is the different category here. So when you isolate the oldest, you reduce the number of infected, but you don't reduce a lot the epidemics. If you reduce the youngest, you don't reduce a lot the deaths because the death was mainly the older people, but you reduce the epidemics. So both are interesting. But this is not really what we wanted to do. But for example, now we can play with many things. For example, what is the benefit or not of the teleworking? But many teleworking are only white collar who are doing teleworking, blue collar, right? Work on the field, so they are not doing teleworking. So in France, the part of white collar is more or less 45%. But the same, so doing teleworking is quite interesting. So it reduces the deaths, the number of deaths, not as much as reducing the isolated, the oldest, but it reduces the deaths, but it also reduces the epidemics. So if you look only, yeah, we cannot see very well, but the epidemics or the white collar itself is not so big, but in the total, it's still interesting. Okay, so what is interesting in this work is that now we can play with many categories, not only age or their position. You can play with all the things. So, for example, the school, what if it was a good thing to close the school, the university, many things like that. Okay, so just to conclude, I think I am exactly on time. So just to conclude, so I hope you have seen that mathematical models were used from very long time to the fight against epidemics. So from the 18th century, probably before, but we don't know. The first paper we have is Bernoulli, but still today, okay, COVID is a great example. So it was interesting also in France, even in the TV show, they were talking about Arnaud, about mathematics. So mathematics is very important, but it's just a tool. It's not it cannot be used as the truth. It's just approximation of models. So this is something very important. When you are using mathematical model, don't forget that this is just a simplification. So it is helpful, of course, it's very helpful, but there are limitations. So they are not always the truth, and we have to be very careful, especially for this kind of epidemics, on how you use the model and what you do. Okay, so I will stop there. Thank you very much. So yeah, I put some reference. If you have any question, I am still there.
Thank you very much. Thank you very much, Professor Mammeri. This was an exposition of the different modeling strategies based on the SIR model. Very instructive exposition. Any questions from the audience? Well, so let me start with Professor Nassif.
Yes, hi. Thank you.
Hi.
Thank you, Professor Mammeri. Thank you, Fatima, for organizing.
You're welcome.
I have a couple of questions. First, I want to thank you for a very nice expose, which, of course, and nice results also. I have a couple of questions, as I said. First, when you have a model of PDE, which is a model a transport equation that you deal with?
This one was so the one with only the daily movement is just a reaction diffusion PDE, and it was surprising because it's quite simple, just a reaction diffusion. It was very nice. But if you want to add also the transport, so the green map, you need also to add a transport advection in your PDE. So at the end, you will have an advection diffusion equation.
So this would be here like a reaction diffusion equation, the simulation that you got.
Yeah, advection, reaction, diffusion.
Okay, so then it's a second order in space.
Yeah, second order in space.
Okay, and it was easy for you to get the coefficients to estimate the coefficients for the
PDE. Yes.
Yeah. Okay.
Because in France we have so for the diffusion quite easy because we know what is the mean displacement of a French citizens. We know, okay, he will move 15 kilometers from his home, so you don't know the way. So okay, so you can get the diffusion coefficient like that, and the transport, the advection, you have exactly from the map directly. You can just download the data from the map and you get your advection.
Yeah. Okay. Now, one thing about your simulation, they indicate that if you are near the French borders, the French frontiers, that is, if you are exposed to to Belgium or to the La Manche or to Germany, then you have really the outbreak is coming from there.
Yeah, you're right. So the simulation were done during a very specific period where the frontier was closed, so nobody crossed the border.
But here they seem not to be closed.
No, there is because you don't see very well. This is a Neumann boundary condition. You cannot cross the border.
Yeah, but the red is coming from the borders, right?
No, this is still France. Yeah. Okay.
I see. Okay.
Yeah, still France. So Belgium is here.
Yeah.
And Germany is here.
But from Belgium up.
Yeah, it looks like, but it's not. Everything is inside France. Yeah.
Yeah. Okay.
Yeah, there's some question. If you put the neighbor country, what you put in the boundary condition?
Yeah. Okay. If you just can you go back to the slide about your model where you have susceptible, exposed, symptomatic, asymptomatic? Yeah.
Yeah, this one we can see here.
So here I think just because you work with, so you have a model whereby you have about 1, 2, 3, 4, 5 compartments, right?
Yeah.
Okay, and then so basically the susceptible, then they are split. So the susceptible become exposed.
Yeah. First.
And then there is a fraction which is not exposed, right?
Yeah, but they stay susceptible. Okay, the one who are not exposed, they stay susceptible. There is no immunity, for example.
Yeah, I'm just asking why do you need this exposed compartment? What does it bring into your model?
Now, in terms of modeling, it doesn't bring a lot. Yeah, I could put, for example, directly you go to this way and this one directly, but it's more in terms of biology, because the exposed compartment is still important in biology because you are infected and you don't know. It's more, okay. It's just to take this into account.
Okay. Now,
because okay, for example, you can make a test. So this is mainly you are in contact with someone. They say, okay, you have to make a test. So you are still not on this one. You just exposed because you were in contact with someone and you have to make the test.
So kind of it's a delay period between becoming.
You can also remove this one and put a delay in your model. It's another way to simulate it.
Okay.
So you are not, so here we put as a compartment, but you can also put as a delay. There's many ways to simulate the latency period.
Now because to compute your parameters, your coefficients, beta, you have several coefficients in the model, beta E, beta IS, beta IA.
Yeah.
So how do you have data for these? Do you have data for the symptomatic and asymptomatic?
No. What we have is the latency period. We know it is around 5 days. And the infection period around 7 days, 7 to 9 days. This is the only thing we have. The rest we calibrate, and we explain that. For example, this is so. And what is also important. So when you calibrate, you cannot compute omega, and you cannot compute beta separately. It's impossible in the model. So what you get is only the product. The W beta E, W beta S, and you don't know very well the proportion. I agree with you. We don't have access to this kind of data, and this is so because when we make the simulation, okay, this is written in the paper that we cannot simulate that. So actually the politicians were interested in the W. So because what they really want to know is that if people follow the rules. So what they want is the number of contacts, but I explained them that this is not possible to have.
Not even a star.
Yeah, even a star. Yeah, this is very important thing because they always assuming that they know S star, but S star is impossible to measure in real life. Nobody knows S star. So in most of the case, they assume that this is the world population, which is a very tricky assumption.
Questionable.
Yeah. But I had a lot of discussion with the medical doctor and with the politician on that. Explain that's okay. You have to be careful because S star, you don't know S star. You can do what you want. You don't know how to measure this S star. You don't know the contact, but still, they love the R0 because it's simple. But they don't understand that most of the things are not measurable in terms of biology.
Anyway, thank you. I will leave the floor now. Thank you.
Thank you.
Please, Professor Murad, can you go ahead?
Hello, everyone. Can you hear me?
Yes,
Yeah.
yes. We can hear you.
Okay, great. Well, first of all, I'd like to thank you for this very nice presentation. Actually, I have some questions regarding, first of all, your model. In your model, you don't actually, you cannot reproduce the generation of multiple waves because you have the system of ODEs. And the coefficients, as you said, you do some calibration to estimate these coefficients, and then your solution will be as you present here on this slide, on this figure. So do you have an idea about some modification to your model in order to reproduce such waves? The waves are not necessarily related to the change in the virus, so they may possibly they are related to the coefficients themselves, right?
Yeah. I totally agree with you. So I don't think I say that you can have a multiple wave with the ODE. I say with the PDE, yes.
Mm-hmm.
But yeah, you're right. So with the model I present, the ODE, if the coefficients are constant, you can have only one wave. So you can prove it. There's only one wave.
Yes.
So and actually what was our motivation when we start to do that is how we can have a multiple wave. So because my expertise is in PDE, so I use the space to have multiple waves. So it was one of our questions. Of course, yeah, if you add mutation in the coefficient, okay, you can have a multiple wave also. This is something yeah, I show here a little bit. So here, so you have one wave, and then it's not really a second wave, but here you have the mutation, and then you can have another wave. So in the ODE, so to get multiple waves, so itself, so our point of view to get the multiple wave, so our point of view is the space and the social category. So if you have different group and they meet and they can meet. So but in the ODE, I think yeah, if the part, but as you say, if the parameter itself are update with time, you can have multiple wave.
Mm-hmm.
So if you take into account some environmental process in the...
Yeah, for instance, if you consider the reproduction number to be a function of the number of cases,
yeah, exactly.
You know, people, they can react. So if the number of cases increases, then people are more, they take more, I mean, they are precautious and they don't go outside and contact everyone randomly.
Exactly.
Yeah.
This is what I was trying to say exactly. So if you take into account the human behavior in the ODE, you can have
exactly. Simply, I think if just you modify your coefficient R0 by or omega, let's say, to be dependent on I think this will be a good job to reproduce waves.
Yeah, actually, I did it with a psychologist, but I didn't put the simulation.
Okay.
But we did that. We take into account the
people mentality.
Peter mortality, if they accept the rules or not. And
Yeah.
you can have this multiple wave too. You're right.
I have another question regarding travelers. So you mentioned travelers when you talked about spatial model. So people, they can move from one side, from one country to another country, or from one region to other region in the same country. Well, you can also, for instance, consider travelers as a source term. I mean, without considering space, just in your ODE system, you can consider as a source term the travelers, and then you can, for instance, by looking at some data from the airport, and you know the number of people coming and the proportion of people that are contaminated with the virus. I think this, I don't know if you have tried something like that.
Yeah. Maybe I didn't explain well this slide. So actually, in the slide you have both. So in each place, you solve a PDE, and the transport between place is a source term. It's just a connectivity matrix between place. So here is a hybrid modeling. So you have PDE for inside the country. Yeah. And explicit exchange between places.
Yes, I see. Okay, now it's clear.
Exactly what you said. Yeah.
Okay, perfect. Yes, great.
But I try to not put any complicated mathematics in my slide.
Yeah, that's fine. That's fine. That's fine. That's great. My last question. Well, regarding the coefficients, you said you make some kind of calibration for your coefficients in order to have an idea about them. Well, when you say calibration, so you compare with real data, isn't it? With observed data?
Yeah, with the data, because so we have so you see all the dots here. So they are the data we get from the government. Yeah. So we
did you make some kind of inverse problems in order to calibrate, or just calibrating by just tuning them manually?
No, this is a Bayesian process. So
Bayesian process. Okay, I see.
So this is not. This is also one question. One thing I explained to many people. This is not just one simulation. Okay. So maybe we can see. I think a bit better here. So there's a basis. So here all the gray curve are good solution. Okay. So I didn't put the. Yeah, maybe I can still. So because it was hidden. So yeah. So I think you can see. So this is the real simulation of the calibration. So each curve is a good curve, and then you have the mean of the parameters, and is a standard deviation.
So you introduce some kind of random variables in your process or not?
Yeah. When to find the
coefficients.
The coefficients, yeah. Okay. When you run your calibration. Yes. So this is not just a deterministic process. This is really
yes, but in your ODE, you just have a deterministic system. You don't have any stochastic variable anyway.
Yeah. No. In the ODE is purely deterministic. Okay. But when you look to the parameter, many parameters can solve the equation. You don't have a uniqueness. So this is what we said before.
Yes, exactly.
We don't know
you don't have uniqueness of choice, right, for coefficients.
Yeah, all of this. So all of these are parameters that works for the simulation.
I see. Okay, that's great. Thanks a lot.
Welcome.
Well, thank you very much. Thank you very much, Professor Mammeri. I think that's it for today. We tired you enough.
Yeah, it's late for you.
Thank you. Thank you very much. So have a good day. Thank you.
Welcome.
Thank you everyone for joining also.
Okay. Bye-bye.